In this video, we will continue our theme of inverse functions and begin discussing the inverse trigonometric functions. So if we think about what the graph of sine looks like, to the left here, note, in general, it does not have an inverse. We can draw many horizontal lines that intersects the curve in infinitely many places. So what we have to do in order to guarantee an inverse is somehow restrict the domain, such as from minus pi over 2 to pi over 2, so that it passes a horizontal line test and every single output is hit exactly once. So if we restrict the domain, we can define the arcsin such that x equals arcsin y is equivalent to saying y equals sine x, but on this restricted domain. And we can see a graph of the arcsin to the right. A little bit of information about it. So if we have y equals arcsin of x, equivalently one could also write this as sine to the minus 1. I will interchange the two accordingly. But note, when you see this notation sine to the minus 1, do not confuse that with the reciprocal of sine. Remember, it is the inverse sine function. The domain of the inverse sine is minus 1 to 1, those outputs of the sine function. And its range would be the restriction of the sine domain. So minus pi over 2 to pi over 2. So let's go ahead and investigate a few examples dealing with the inverse sine function. For the first example, let's find the exact value of arcsine of minus 1/2. So as a starting point, arcsine of minus 1/2 is going to be, we'll say an angle, call it theta, such that sine of that angle is equal to minus 1/2, and the theta, recall, has to be between minus pi over 2 and pi over 2. So that's the key thing to recall. Whatever output we have for the arcsine function, it's always going to be in this interval from minus pi over 2 to pi over 2. So we think in that interval, where is sine equal to minus 1/2, and there's only one value, and that value is minus pi over 6. So arcsine of minus 1/2 is equal to pi over 6. So similarly, let's now investigate the cosine of arcsine of 1/2. So cosine of arcsine of 1/2. So for an example like this one, we really want to work from the inside out. So I'm going to do a bit of work here to the side. I'll go ahead and define arcsine of 1/2 to equal some angle theta. Now note in this case, you could tell me immediately what that value is, but I want to approach this a bit more generally so that if maybe instead of 1/2, say it was 2/3, we would have a similar approach that we could use. So what this tells us is that 1/2 is equal to sine of theta, and I'm going to draw a right triangle corresponding to this statement. So we have our angle theta, right triangle, sine of theta is 1/2, so this remaining leg should be square root 3. So cosine of arcsine of 1/2 is equal to cosine of theta, and looking at our right triangle, we think cosine of theta is adjacent over hypotenuse. So square root of 3/2. Now note equivalently what one could note, similar to our work above, is arcsine of 1/2 is pi over 6, cosine pi over 6 is root 3 over 2. But note this method is a bit more generally applicable. Similar to the inverse sine function, we can define the inverse cosine function. If we consider the graph of inverse cosine, we see that it most definitely does not pass the horizontal line test, does not have an inverse in general. But if we restrict its domain, the typical thing is 0 to pi, it will pass the horizontal line test, and we will hit every possible number in the range of cosine, minus 1 and 1. So we can define x to be equal to the arc cosine of y, and note, equivalently, x equals arc cosine of y would be cosine inverse of y, so cosine to the minus 1. We use the notation interchangeably, but remember, raising to this minus 1 power is not 1 over cosine. And how we define this is we say this is equivalent to y equals cosine of x, with x in that restriction for the domain. So in terms of range, domain and range for the cosine inverse, its domain is from minus 1 to 1, and its range is from 0 to pi. Similarly, we can think of the inverse tangent function. So for the inverse tangent, once again, we need to somehow restrict the domain of the tangent function so that it is 1 to 1, or passes a horizontal line test. If we look between minus pi over 2 and pi over 2, it will. And we can once again define the inverse function. So we can think x equals arctangent, or think tangent to the minus 1 for tangent inverse, is equivalent to y equaling tangent of x with the suitable restriction. So in terms of the tangent inverse, looking at the graph, we see that the domain is all real numbers corresponding to those outputs we have for tangent. And the range goes back to that restriction of the domain for tangent. So minus pi over 2 to pi over 2. Also of interest with the inverse tangent function are several associated limits. Note that we can talk about the limit as x goes to infinity and minus infinity. As x goes to infinity, the limit is pi over 2. And the limit as we go to minus infinity is going to be minus pi over 2. So two nice limits associated with the arctangent function.